This video is a follow-up to my previous video where I installed a lithium iron phosphate battery into this Suzuki SV1000. The battery that I installed last time was an 8.4 amp hour 30C discharge rate battery. Today I'm going to install a battery that is half of that. It's 4.2 amp hour capacity times 30C discharge rate. And we'll see how good is the battery at cranking this. It's 1 liter, 2 cylinders motorcycle, so it requires a pretty beefy battery to operate. I'm going to attempt to start the motorcycle with that battery, and I'm going to see how much current is being drawn. And at the end I'm going to give some recommendations of how to install a lithium iron phosphate battery into a motorcycle on the cheap. So for half a year I've been riding the motorcycle with this 8.4 amp hours lithium iron phosphate battery that I bought from Hobby King. It has a 30C constant discharge rate and a 40C burst, which translates into 250 amps constant and 336 amp burst discharge rate. In the previous video I measured the actual current drawn from the battery, and I think it was a little over 400 amps for a quarter to 1/10 of a second when the ignition is turned on, and then it drops to about 100 amps, so the battery was fairly comfortable with it. So in the half a year the battery did not puff. When these batteries are abused, they tend to puff. This one is still flat. I checked its amperage, its capacity, and it's actually more than 8,000 milliamp hours. I did not want to discharge it fully. I discharged it at 2 amps until it was 12.5 volts. You can discharge these batteries up to 8 volts, but the amount of battery capacity between 12.5 and 13.5 is much more than between 12.5 and 8 volts. So probably I left, I don't know, 10% in there. So I think it still holds the full capacity, the full 8.4 amp hour capacity that it was sold with. So some people were asking if the smaller battery. Oh, and in the original video I actually said that the battery that prompted this whole endeavor of trying a lithium iron phosphate battery, this battery tender for $100, I said that judging by what people say in the comments and by its cranking amps, it's most likely this battery, the smaller battery. And the smaller battery is actually, it's half of the capacity of the big battery, but it's also half of the cranking current, because here the way you see the current that it can output is the capacity times the discharge rate, and both batteries have 30C discharge rate. Yeah. So as you can see, it's well, half of the other battery. It's half by weight and both half by size, and I was not sure if it's able to start my motorcycle and how well it's gonna work. So let's hook up the smaller battery and try to start the motorcycle, and then I'll hook up the bigger battery back and we'll compare the two. You can see the small battery inside the battery compartment of this Suzuki SV1000. It's about, I'd say, quarter of the stock lead acid battery in here, because you can fit 2 of them here and 2 by height. It's 556 grams or 558 grams, a little more than 1 pound. So it's a fraction of what the original battery weighs. Yeah, let's hook it up directly so that so the bigger battery at some point was connected through a BMS. Then the BMS actually the MOSFETs on the BMS burned, or something bad happened to them. I still didn't figure out what exactly happened. So I'm currently connecting the battery directly to the motorcycle, but this shouldn't be a problem because the motorcycle doesn't overcharge the battery, and if I don't over discharge the battery, it should be just fine. So connect the positive wire first and the negative wire second. Disconnect them in the opposite order. The small leads here, I made those, and the other ones are just you know, stock motorcycle clamps that were hooking to the lead acid battery. Okay, let me go grab the keys and we'll try to start it. I actually fully charged the battery before trying this. The current voltage per cell is 3.42 to 3.46. It's interesting, when the battery is fully charged, I charged it to 14.4 volts. This is actually 3.6 per cell. All the cells were balanced at 3.6, but when it discharged by itself to 3.4 volts, the cells actually have different voltage on them. I had to wait for that airplane to fly away. I wanted you to hear this motorcycle in full glory when it starts. One thing that I forgot to mention is that the smaller battery has a 10 gauge wire in it. The larger battery had an 8 gauge wire. So, you know, Hobby King and whoever created the battery really designed this battery for lower current. Okay, let's see how this one goes. I'll try to start it 3 times with this battery. I did not start this motorcycle today, so yeah, this is a cold start on a rather warm day. That's still a cold start. And third time. I actually think the second and third time the battery had more trouble starting the motorcycle. I'm not quite sure why, because I expected it to be the opposite. These batteries, the lithium iron phosphate batteries, they like the manufacturers of those batteries that sell them for motorcycle, they say that in cold weather you should warm them up, you know, leave your ignition on for a minute before you start, because it will, I don't know, rejuvenate the battery, and then it will be able to deliver more current. But I think in the previous experience that I did with this battery, and now the second and third attempt to start the motorcycle, were a little bit harder on the battery. I'm going to put back the old and bigger battery, and I'll let you compare the cranking amps on those, cranking power. So this is back with the 8.4 amp hour battery that I was riding up until now. I think you can hear that the larger battery definitely has easier time starting this motorcycle. I'm probably abusing it by starting it so many times. Okay, let me get my oscilloscope, and we can try to estimate the current that is being drawn from the motorcycle when we start it with the old and with the new battery. So I want to measure two things. First, I want to measure the current that is being drawn from the battery when the motorcycle starts. And the second thing that I want to measure is how low the battery voltage sags when the motorcycle starts. So to measure the current, I need a shunt. You know, I have this small clamp current meter, but one, it goes only up to 100 amps, and two, it doesn't have inrush current measurement, so I cannot really use it. So what I'm going to do is I'm going to measure the voltage drop across a shunt, and then I'm going to measure a smaller current and you know, do the correct ratio. I'll show you the math on a piece of paper. So first I want, so for the shunt I will use this this red lead that goes from the battery to the motorcycle. It's not long, probably I don't know, 30 centimeters, 15 inches, maybe lower, maybe smaller. And I drew a small sketch here of the battery. So this is the negative terminal, goes through all the 4 cells, comes out to the positive terminal, and this is the balance lead. So the balance lead, it just gives you the voltage of all the cells if you measure across here, and also it can give you the voltage of the entire battery. So I'm going to do two things. I'm going to measure the voltage drop across this wire, the positive on the battery to the positive that the motorcycle gets, and this will allow me to measure the current. And I'm also going to measure to see how low the voltage across the edge terminals on the balance lead get, to see how low the battery sags. So to get my initial measurement, I connected the voltmeter, negative of the voltmeter to the positive of the terminal of the motorcycle, and positive of the voltmeter to the positive of the balance lead. And I'm going to start the motorcycle ignition, but I'm not going to start the cranking. So it will draw some current for the headlight, but it will it's going to be a pretty low current. Just a second. Let me turn on my multimeter first. Okay, there we go. So now the voltage drop is 0 because there is no current across this wire. So it's expected. Okay, and it settles at 12 millivolts. And 12 millivolts, we can measure the actual current that the 12 millivolts correspond to. I want DC, and I will zero it out here. It's almost 0. What? Oh, it's 2 amps. Sorry. DC. So 0, 0. So it says that this wire draws 10.5 amps, 10.5 amps. So 10.5 amps correspond to 12 millivolts with this battery. So I hooked up my multimeter across the same terminals, positive on the balancing lead to positive of the motorcycle, to see the voltage drop across that thick wire. And what I have here is it's in rolling mode, so we'll see the current changes, the voltage changes here, they correspond to the current changes. And then it has 100 millivolts per division. So we expect this motorcycle to draw close to 400 amps when it cranks. 400 amps, so 10 amps correspond to 12 millivolts, so it's almost 1 millivolt per amp. So it should be 0.4 to 0.5 volts, half a volt of voltage drop. And here we have 1, 2, 3, 4. Between here and here, this graph will jump when we crank the engine. Well, let's see how it goes. And this is with the small battery in there. yeah, zoom in a little bit. There is our ignition. So yeah, it's 3, 4, 5, between 4 and 5, between 0.4 and 0.5 of a volt of voltage drop across that terminal, and the entire duration of this thing is it's 0.10 of a second per division. Sorry, I don't see it very well here. 3, 6, 9, almost a second total. So you know, first a tenth of a second it was higher, first a quarter of a second, and then it settled at about 100 amps. Let me also measure the voltage stack on the battery, and I'll save all these printouts, and then we can go to the bench and analyze them. So this is the same oscilloscope in the rolling mode, but connected across the balancing lead. So it sees the current at the battery cell terminals, and it's changed to 2 volts per division. And here the voltage right now is so this is 12 volts, and that is 14 volts. It's more than 13 volts in there, between 13.5 volts about. And we'll see how low this voltage drops when we start the motorcycle. So I'm turning ignition on. Not that bad. So this dropped all the way to this line, and this line is about 6 volts. See if it actually hits 6 volts. Yeah, it didn't hit 6 volts. So this is 6, this is 8. Very close to 6 volts. I call it 6 volts. Let me save it. And I'll do the same experiments for the other battery, and I'll print all of them, and we'll go to the bench and see what we can see. So this is, I decided not to do it offline, I decided to show you guys how I do it. This is the larger battery hooked up, and this is voltage across the larger battery. We can see how low this one will drop. The small battery dropped to 6 volts. Let's see how low this one goes. Just let me make it less. Okay, go. So as you can see, it's the same 2 volts per division. This one is 6 and this one is 8. So it dropped less than 8, but not much less than 8. So the other one dropped to 6, this one dropped to 8. Which is nice. Yeah. It means that the battery was not as stressed as the other one. And now I'm going to measure the current, and I'll get back. And this is the oscilloscope connected across the positive lead that goes from the battery to the motorcycle. I will see the voltage drop across that lead, but you know, beware that because the lead includes part of the motorcycle of the battery wire, the voltage drop will not correspond to the smaller battery, and we'll have to recalibrate it to see that 10.5 amps of current, how much voltage drop it corresponds to. Anyway, here we go. So you can see here It's the same 100 millivolts per division, so this is 0.3, 0.4, 0.5. This is half a volt, and it's a little bit more than that. I'll have to measure again the voltage drop of when just the headlights are on, and we'll see that what that corresponds to. I'll save the waveform and I'll get back to you. I wanted to illustrate what I previously said. So now the big battery is connected back, and I'm measuring the voltage drop across the positive lead from the positive of the balance to the positive of the motorcycle, and we'll be able to see that it's 0. So it's the same 10.5. It's 10.6 volts now. I don't know exactly why, but this 10.6 amps correspond to, now it's 10 millivolts of voltage drop. The other battery had 12 millivolts. So the difference is that this positive lead from the battery, it's shorter and it's 8 gauge wire. The other one was a little bit longer and it was a 10 gauge wire. And it's actually, I turned off the headlights, and it's actually pretty strange because it goes, well, okay, it goes higher now. This is expected. But it went down to 11 and then it got back to 10. And I guess we'll count it as 10. 10 millivolts, the same. It's 10.6 amps now for some reason. So I wanted to recap what we have seen so far. I know my printer sucks, so you don't have to tell me that. So this is for the smaller battery on this side, and the larger battery on the other side. This is the graph of the amperage, and this is the graph of the voltage of the battery. And yeah, they don't exactly correspond because it's two different runs. I didn't take the same. I didn't take them from the same start of the motorcycle. But there are several things that I wanted to point out. So the peak voltage drop across the positive lead was 0.47, I estimate 0.47 for the small battery, and our measurement was that 10.5 amps is 12 millivolts. We measure 0.47 volts here of voltage drop, and I calculated it's 411 amps. So at this point it's 411 amps, and this is pretty much, as far as I understand, the short circuit of this battery. And then the amperage that's drawn from this battery drops. It drops to about half, so from 5 divisions to 2.5 divisions for the first tenth of a second to 2/10 of a second. So, you know, anywhere between 400 and 200 amps in the first 1/5 of a second, in the first 200 milliseconds. And the voltage drop, and the voltage on the battery itself drops to 6 volts, which is, you know, rather low. And another interesting thing that I didn't notice originally was that the overall start time of the motorcycle is much higher on the smaller battery. So it's 0.9 of a second here, and 0.8.5 of a second here. If we look at the larger battery, we see a quite different picture. So the peak is voltage drop is 0.55 volts, and our measurement where the 10.6 amps is 10 millivolts. We see a voltage drop of 0.55 at tops. This corresponds to 583 amps. You know, that's a lot. I don't know if it's a fluke or it's you know, it's much more than the battery was designed. And for the small battery, just a reminder, it was designed for 126 amps constant discharge and 170-68 amps burst. Burst means 10 seconds. So this is, you know, 0.2 of a second, and my gut feeling tells me that this does not damage the battery, even it exceeds the even though it exceeds the spec by a lot. but I'm planning to test it. I'm planning to put this battery in my motorcycle for another half a year and ride it and see how it goes. Yeah, the other battery is twice as much, right? So for the other battery, it's 250 constant, 336 burst. Burst is again 10 seconds, and we see a 580, almost 600 amps peak, and then probably half of that is 250, 290 amps. So yeah, I think the other one is completely comfortable handling the start of the motorcycle, no questions about it. This one, oh, and also the start time is smaller. This is half a second, this is 0.7 of a second, and this is 0.6 and a little bit of a second. So yeah, this is 0.9 of a second start time, this is 0.7, and this is 0.6.5 for another start. And the voltage also sags not to the 6 volts, but it sags to the 8 volts. Yeah, I think these are interesting results. This number 583 exceeded my expectations, and exceeded the spec of the battery by almost a factor of 2. I think this battery has a little bit of trouble, but I expect it to work. I don't expect in half a year it to puff. And it's half of the price of the bigger battery. So this battery is $41, and this was 80 something. Yeah, this one is, the bigger one was 82 and the smaller one is 41. And so the Suzuki, actually the 1 liter 2 cylinders is pretty demanding of the battery. So, you know, if you have a smaller, if you have a 250cc motorcycle, I think, you know, you just go with a smaller battery, no questions asked. If you have a I don't know, a Gixxer 600 or something, both of them might work. I think the smaller might work. If you have something bigger than my motorcycle, I would just recommend you to go with a larger battery. There are 2 more things that that you need to consider that I forgot to mention. One is the current that the motorcycle charges the battery at. So the lithium iron phosphate and lithium batteries in general, they like when they are charged at 1C. This means 1 capacity. For 8.4 amp hours battery, it's 8.4 amps, and for 4.2 is half of that. So if the motorcycle charges the battery at, say, 10 amps, then that exceeds the charge current for the 4.2 amp hour battery by a factor of 2, which is not good. It will cause, yeah, the battery will degrade prematurely. That's one thing, and I'm going to measure that. And the second one is the top voltage, where the motorcycle stops charging the battery. And mine says that it's anywhere between 14 and 15 volts. And I'm going to measure it now. I need to run the motorcycle for a longer period of time to do that. Okay, so let me explain my setup a little bit. The voltmeter is measuring the voltage on the motorcycle terminals. That's what the motorcycle sees. The clamp is measuring the current across that goes into or out of the battery, and it should be sitting at 0. And there is a small balancing lead in there, so that when it engages per cell, when the cell reaches 3.6 volts. It starts to discharge that cell to make sure that cells don't go above 3.6. So I discharged the battery a little bit by running the headlights for a minute here, so that we can see what's the current that's being put into the battery by the motorcycle, and also we will be able to see what's the voltage that the motorcycle will put on the battery. So as I said, ideally this should not exceed 4 amps, and ideally you'd have the motorcycle stop at 14.4 volts. So you can see that have a light in here. You can see that the motorcycle is putting 7 to 8 amps into the battery, which exceeds the charge rate that this battery would be happy with. And it will take about a minute for this battery to charge, because I ran it for a minute, taking 10 amps out of it. So it should run about a minute to put, a minute and a half to put all the charge back. So the spec says that for lithium iron phosphate batteries, they are full when the voltage per cell is about 3.33 volts. But if you put more voltage on the cell, it will not damage, and it will not cause damage. There are different papers out there. Some say 3.65. I have a BMS that allowed the cells to go up to 3.85 volts per cell. 3.6 is 14.4 volts. 3.65 is 14.6 volts. So the voltage on the battery slowly goes up as the motorcycle puts charge into it. So it took a couple of minutes, but the voltage on the battery now is 14.5 volts. You see the balancing circuit starts to engage, and the current dropped to 0.3 amps roughly. Yeah, it's interesting why the balancing circuit engaged when I turned the motorcycle off and didn't engage before that. But you saw it, bring all the cells to 3.6 volts, and the overall voltage translates to 14.4 volts. The clamp meter, I think it's a drift, should sit at 0, because I believe no current is being drawn by the motorcycle. Let me take it off. Yeah, you can see here it's not sitting at 0 exactly. Maybe it warmed up or something. I put it back on. Yeah, it's still showing something. I don't believe that's right. So yeah, you saw that the maximum voltage there was 14.5 volts. I've seen in the previous run it get up to 14.6 volts, and when that happens, all the balancing circuit engages and starts to discharge the battery. The problem is that this balancing circuit gets really hot when it's active, so I will not be able to leave it there always, because it will melt through the heat shrink that I was planning to put on top of it. Maybe I'll use the other balancing circuit instead. Yeah, hope you find that useful. You have to measure the same thing on your battery. Oh, and another thing that I wanted to point out, that we saw 7 to 8 amps here of charging current, but actually for the bulk of charge, the voltage was at 13.6 volts. And the charge current was about 5 amps, so it's not as bad as before. 5 amps this battery will handle, of charge current will handle quite happily. 8 is a little too much. see that 3 out of the 4 LEDs started to light up because the total voltage exceeds 14.4. Some of the cells have more than 3.6 volts, and the balancing circuit is discharging them now. The current is fairly low. I decided to stop it because this balancing circuit, it gets quite hot when it operates. So what you can see there is the first two cells, they drop to 13.6 volts, and the balancing circuit is going to stop, and then the other ones are going to drop to 13.6, and they're going to stop too. So yeah. And the balancing circuit, it finishes when the battery is about at 14.4. So what this showed is that the motorcycle stops, puts the voltage on the battery at 14.6, and this is a little bit disappointing because I will not be able to use this balancing circuit all the time. If I use the balancing circuit all the time in there, it will overheat and it will melt. Especially I wanted to put it in a heat shrink tube so that it doesn't touch accidentally something, because there are exposed contacts in there. I either need to come up with a heatsink for it or just not hook it at all. Okay, hope you find it useful.